In this video, we will see a logically precise formulation of the pumping lemma for context-free languages that may be helpful while proving certain theorems. The pumping lemma states a property of context-free languages, but it is almost never applied to context-free languages. Instead, it is applied in the contrapositive to languages believed to be non-context-free. Let's tinker with the lemma and try to derive a valid contrapositive. Beginning with the original lemma, let's mold it into the language of predicate logic. We can add quantifiers where it seems appropriate. Each of the variables of the lemma requires some quantification, either a there exists or a for all. Now that the quantifiers are added, the formula is looking slimmer, and we can condense it further by adding more algebraic notation. And now the consequent looks in a more pliable form to be negated. Negating P is the easy part, so let's check that off first. The negation is simply that A is not a context-free language. And for the negation of Q, let's first negate each of the quantifiers. Each there exists becomes a for all in the first half of the statement, and nothing else needs to be negated. I will get back to why that is in a bit. But first, let's look at the three conditions of the lemma. We have to be careful regarding the conditions because there is an and between each of them. To negate them, we will propagate the negation inwards, so to speak. So each of the conditions gets negated, and don't forget that the ands between them convert to ors. This tells us that either of the three conditions have to hold in negated form. So let us add the word either for more clarity. Alright, so the negated formula doesn't look so bad. What this statement is saying is that there exists a string such that no matter how you divide this string into UVXYZ, one of the three conditions of the original lemma won't hold. So first we pick a valid string such that for any arbitrary division of the string into UV, X, Y, and Z, either pumping the string S takes it out of the language, or the substring Vy is empty, or the substring Vxy is longer than the pumping length. At least one of the three conditions must hold for each distinct assignment of UV, X, Y, and Z. For many assignments of UV, X, Y, and Z, conditions B and C will hold. This merely relies on the lengths of the substrings Vx and Y being either 0 or larger than the pumping length. For the rest of the cases, condition A is the one that will need to be tackled. Condition A requires some ingenuity. It is the proverbial proof of the pudding. The other two conditions are trivial. That is why we always only do examples that prove condition A while holding B and C as false. A pedantic proof, of course, would also spell out the cases where B or C are true, but we will always skip those in favor of the more interesting case. So back to the negated formula. Why were the algebraic statements in the first half of Q not negated? While deriving a negation for Q, why did we not switch S greater than P to S less than P? The reason has to do with the fact that this statement has an if-then structure. To negate an implication, we have to show the consequent false while also showing the antecedent to be true. Hence, we only negated the three conditions and let the first part be as it was.